So we define the vector n, the normal vector that's orthogonal to this plane. That means that it's perpendicular to any vector that can be drawn on that plane. If you have a vector there, that angle is 90. If you have a vector that's there, that angle is also 90. And so from that, if that's true, then we could say that it's orthogonal to these 2 points and a vector drawn there. That vector, let's call that vector P naught. P naught. That vector is orthogonal to vector n. And do you remember what the dot product of 2 orthogonal vectors are?
It would just be like the x times x, the other x plus the y times the other y. And since we're doing 3-dimensional, it would be z times the other z.
But if they're orthogonal to like perpendicular vectors, the dot product, you know what it is, Josh?
It's okay. I was thinking it was 0, but I don't know why.
Yeah. It's kind of hard to explain, but this thing we're you'd have to like basically go into like proving it using geometry and stuff. But for our purposes, that's not necessary. If that's true, then that means that the vector P naught, which has the, if you remember from before, it has the coordinates or components x minus x naught, comma y minus y naught, comma z minus z naught. And that dotted with the vector n with components a, b, and c, it's going to equal 0. Which means that a x minus x naught plus b times y minus y naught plus c times z minus z naught.
I know.
That's just going to be 0. Or ax plus by plus cz is equal to ax 0 plus by, or ax naught by naught plus cy naught.
You should make it start at 4 is what
And let's say that this is a function
Wait, Diego?
Yes?
Isn't it c z naught? Yeah, sorry about
Yeah,
that.
my bad. Nice catch.
Oh, thanks.
And so, if we assume that we vary this with just respect to x, y, and z and naught, x naught, y naught, and z naught, assuming that those are constants, then we could just say that this whole thing is a constant. And let's call that constants. Let's see, we have A, we have B, we have C, let's call that D. And so that is an equation for a plane in the 3-dimensional world, I guess.
So what exactly does that constant represent?
D
So
is just,
D.
it's just a constant. It's like the y-intercept essentially, except
Okay.
for a plane. But if you look back, that's what it relates to. It's, if you have a point, and then there's like a dot product of the coordinates of the point and the components of the vector, then you get D.
And would it be practical to like set d equal to the x naughts, y naughts, and z naughts, or it just doesn't really make sense?
For this, I believe it's practical, so it looks easier, because that looks a lot neater than that.
No, I'm just saying that setting d equal to a times x naught, like the stuff that you underlined, would it make sense to set that equal to d, or
Yeah,
just,
that is D.
that is d?
Yeah.
But would that be
X naughts and Y naughts, not X's and Y's.
Would that make sense though, to like set d?
Yeah, because this is all X naught, Y naught, Z naughts, those are constants.
Okay.
Or we're choosing that they're constants, whereas X, Y, and Z, or the actual function. Those are the inputs, those are the x, the y, and then the z.
Do
Wait,
you have
hold on.
nice notes? I'm sure you do.
Yeah.
Oh, are you guys
So,
like
does this
Oh,
Yeah.
here, would this make sense to point out, or is there no use for this?
Yeah. So as was previously stated, we had the dot product of p naught and n, the two vectors. And so after simplification and isolation of the x's and the y's and the cz's, we were left with this, saying that ax naught plus by naught plus cz naught is a constant, and that's equal to this. AX plus BY plus CC.
What is this?
Oh, so like both of those equations are,
In a sense, but if we were to try to make an equation for a plane, we would only want one set of variables, not two.
and you would want you would want to make like an an equation where you have a constant equals
I mean, kind of.
three sets of constants added together.
Exactly, because it's just two constants, it's like two equals two essentially.
Yeah.
Yeah,
We don't have that problem.
And so instead of writing this, which gets a bit troublesome, we could just write D, and D is equivalent to ax naught plus by naught plus cz naught, which is where we got the D from.
So close.
And if we assume that x and y and z are all variables, then all we need to find the equation of a plane is one set of coordinates of a point on that plane and the normal vector. And that's it. So let's do an example. Let's find the equation of a plane with a coordinate point P on it. Let's say 1, 2, and 3. Keep it simple, you know.
okay.
And it's normal to vector n. And let's say that is, I don't know, 4, 5, and 6. I know, very creative. Now, if we wanted to find an equation of a plane such that the normal vector has points 4, 5, and 6, and there's a point P which is at 1, 2, 3, we could just plug that into this equation, and we would get that A, which is the point of P, or I'm sorry, A, which is the components of the vector n in the x direction, which is 4, times x plus b, which in this case is 5, times y plus 6 times z is equal to d. But d, as we stated before, is 4, what is the normal vector in the x direction, times the x coordinate of the point P, plus 5 times 2 plus 6 times 3. And what is 4 plus 10 plus 18?
32.
32. So if that's D, and this is equal to D, we could say that as a result, 4x plus 5y plus 6z is equal to D, or 32. And that is an equation of the line with the points P 1, 2, 3, and a normal vector 4, 5, 6.
So if 32 is kind of like the intercept, what exactly is the intercept? Does that mean like, so with respect to like x, y, and z, where do they Is it that 30? No, I don't really know.
Well, there
Like if you
is-
graphed it out, like
If you graphed it out, that would be difficult because you could just pick any point, whether it's there, or there, or there, and these x naughts, y naughts, and c naughts would all change. So there's less concrete meaning in multivariable.
of an
it's
intercept.
just- yeah.
It's
sort
not
of the
like
sum of
oh,
intercept.
it's not like
Except
oh
times
there's an x intercept, y intercept. It's not really like that. There's
Yeah, not necessarily. Alright. How is this? Pretty easy?
so far, yeah.
Yeah. Child's play. Let's do a hard one, alright?
All right, I got you.
This might take a bit of creative thinking and solving. What if I told you there's a plane with points P, Q, and R with coordinates of 4, -3, 1 for point P, 6, -3, 7 for point Q, and R has coordinates 1, 2, 2. My mistake. This is supposed to be -4 for the y components of point Q. Do you have any idea how to convert that information into what we have so far?
Well, I mean, I'm assuming that you can't just do like an xp minus xq minus xr. That would not really work.
Yeah, not necessarily.
Not necessarily.
Instead, if you have 3 points on this plane, let's say point P is there or something, Q, R.
Oh, then they kind of form a
They
shape
kind
if you put them together, I guess. Is the idea to connect them all with
In
a
a
line?
sense. You don't need to connect them all, just, well, if we create a vector PQ from P to Q, and the vector QR from Q to R.
So are you making like a dot, sort of like a dot product of all the vectors possible?
On a dot product, what's a property of the cross product? It's orthogonal to any of the vectors, or to both of the vectors, right?
Mm.
The normal vector is also orthogonal to those two vectors.
Oh, so that,
So if we do the cross product of two vectors, that gives you the normal vector.
oh, so you get another normal vector.
Yeah. Or we get a normal vector from that, because we don't know the normal vector yet.
Oh, so you'd have 3 separate normal vectors, sort of.
Only two.
Only
Only
two.
one. Only one normal vector
Only one normal vector?
and 2 vectors on the plane. Because
Oh,
Q and
because
R
there's,
and P and Q are on the plane, so any vector between them are also on the plane.
would you not have a vector that goes from R to P?
You could, but it's not necessary because this is all the information you need. You could like do that, I guess.
Would
and then
you,
you'd have
could,
like 3 normal vectors.
could you show the work as to why
For all of
there would, or would that be too much?
Wait, I'm sorry. The work for what?
No, the work to show that you only need one, that one n vector.
Okay. Okay, I'm gonna solve for the vector PQ and the vector what? PR and the vector QR. And the vectors would just be the differences in the coordinates. So for PQ, 6 minus 4 is 2. Negative 4 minus 3 is negative 1. 7 minus 1 is 6. For PR, 1 minus 4 is negative 3. 2 minus negative 3 is 5. 2 minus 1 is 1. QR, last one. 1 minus 6 is negative 5. 2 minus negative 4 is 6. 2 minus 7 is negative 5. So, should I find all 3 possible normal vectors?
Pretty much.
Okay.
And then, you know, since you said that you don't really need all 3, like explain why you only need one of them. You don't need all 3.
So, for one of them, let's say we want to find the normal vector at P. That would be the cross product of all the vectors using P as a point. So that would be PR, or PQ, crossed with PR, or yeah, PR. That's equal to the determinants of I hat, J hat, K hat, and then the components of PQ, 2, negative 1, 6, and PR, negative 3, 5, 1.
And just to, you know, clarify, I hat, J hat, K hat, it's kind of like the X direction, Y direction, and Z
Yeah.
direction.
Those are the unit vectors in each of the directions. I hat is the vector with coordinates 1, 0, 0. J hat is 0, 1, 0. K hat is 0, 0, 0, or 1.
Okay.
And so to find the determinants of that, we would do I times negative 1 times 1, which is negative 1, minus 6 times 3, or 6 times 5, my mistake. Minus J hat of 6 times negative 3, which is negative 18, minus 2 times 1, minus 2, and then plus K hat of negative 1 times negative 3, 3 minus 10. And so that's equal to negative 31 I plus 20J plus, minus 7K. Or you can write that as 31, 20, negative 7.
Wait, how did you get those numbers again for when you did the determinants?
To find the determinants,
Like, how'd you get, like for I, how'd you get
for
negative 1 minus 30?
For I,
Mm-hmm.
you just do the determinants of a small matrix. That doesn't have any of the components that are in the same row or column. So you just cross those out, and then you just want to find the determinants of this. And to find the determinants, it's the product of those two from the top left to the bottom right minus the product of these two,
Oh, I see.
which
Okay.
would be the top right and the bottom left.
Mm.
So that's negative 1 times 1, negative 1 minus 6 times 5 minus 30.
Okay, and then it's the same thing for J hat and K hat.
Yep.
Okay.
And then for PQ, cross with QR, we do the same thing, I, J, K, and then PQ, 2, negative 1, 6, QR, negative 5, 6, negative 5, and that's equal to I hat times 5 minus 36, negative 31, plus J hat, I'm sorry, my mistake, minus J hat of 6 times negative 5, negative 30, minus negative 5 times 10, so negative 30 plus 10, negative 20, plus K hat of negative 1 times negative 5, 5 minus 2 times 6, 12, so 5 minus 12 is negative 7. And this is the same thing as writing it in vector notation as negative 31, negative 20. Oh, negative, that's positive 20. Times 30, and then negative 7. So, should I go over the last possible unit vector, or could you take my word for it? Should I go over the last possible normal vector, or do you think this is enough? Like lack of coincidence that these two are the same.
Yeah, they're very the same.
Yeah.
Okay.
So we know that those are the unit vectors. So this is equal to n, the normal vector. Now we just plug this back into this equation with a, b, and c, and we're given a point p, q, and r, but does it matter which point we use?
No, not really.
Oh, not really. I'm just gonna go with p, let's say p with x naught, y naught, z naught. So ax is so that would be 31 times x, 31x plus 20y minus 7z is equal to a times x naught, 124 plus b times y naught,
Negative 60.
negative 60 plus c times c naught,
Minus 7.
that is negative 7.
So then
And
that
that's d, same thing as d. So 31x plus 20y minus 7z
I'll be
is equal to
57.
50, yep, 57. And that's the equation of a plane that intersects all of these points. And we found that by creating vectors between these points. And the vectors all lie on the same plane. So if we find the cross product of any two vectors, we're given a vector that's orthogonal to the plane.
And then you could use, oh yeah, you could use the cross product and all the determinants
Yeah,
to figure out
the n, the normal
n.
vector. And then, yep, that's basically it.
Okay. And I feel like I have to say this again just to remember it, but the x, y, and z, those are like the functions, and then the x naught, y naught, and z naughts, those are the points. They're like the intercepts that you use,
Yep.
sort of,
Yeah,
right?
kind of.
Kind
pretty
of.
much.
But it kind of makes sense.
Yeah, it does, yeah.